October 19th, 2017. At the Pan Stars one observatory perched atop the Haleakala volcano in Hawaii, astronomer Robert Warwick is scanning through the night's automated survey images when something catches his eye. A faint point of light moving unusually fast across the sky on a trajectory that doesn't match anything orbiting our sun the way it should. At first, the object is logged simply as another asteroid candidate, but as more observations pour in over the following days, and astronomers around the world calculate its orbit with increasing precision, it becomes clear this is not another asteroid at all. This object is moving too fast, on a path too extreme to be gravitationally bound to our sun. It arrived from somewhere else, from another star system entirely, and is now the first object of its kind ever confirmed by human astronomers. An interstellar visitor, passing briefly through our solar system before continuing on its way back out into the galaxy, never to return. Astronomers would eventually name it Oumuamua, a Hawaiian phrase roughly meaning a messenger from afar arriving first, chosen deliberately in honor of the telescope that found it. In the years since that October night, this strange little object has become one of the most debated, most scrutinized, and most genuinely mysterious objects ever observed in the history of astronomy. This is everything we currently know about Oumuamua. In the days immediately following its discovery, astronomers scrambled to point every available telescope at the newly found object before it faded permanently out of view. Oumuamua was already moving away from the sun by the time it was spotted, meaning the observation window was short, perhaps only a matter of weeks before it became too faint, even for the most powerful ground-based telescopes to track any further. The first, most fundamental question astronomers needed to answer was simple. Where did this thing actually come from? By carefully tracking Oumuamua's position over several nights and calculating its precise trajectory, astronomers determined its orbital eccentricity, a mathematical measure of how stretched out an orbit is. A perfectly circular orbit has an eccentricity of 0. Earth's orbit, close to circular, sits at about 0.017. Even long-period comets swinging in from the distant edges of the solar system on wildly elongated paths typically stay below 1. Oumuamua's eccentricity was calculated at roughly 1.2, comfortably above 1, meaning its path wasn't really an orbit around the sun at all in the traditional sense. It was a hyperbolic trajectory. The object was moving too fast, at exactly the wrong angle, for the sun's gravity to ever capture it into a bound orbit. It had fallen in from interstellar space, swung around the sun once, and was now on its way permanently back out, never to return to our solar system again. This made Oumuamua the first confirmed interstellar object ever detected passing through our solar system, the first direct physical evidence that material from other star systems does, in fact, occasionally drift through our own cosmic neighborhood. This alone would have secured Oumuamua's place in astronomical history. But the deeper astronomers looked, the stranger the object became. One of the earliest and most striking findings involved Oumuamua's brightness. As the object tumbled through space, telescopes recorded its light curve, a graph of how bright it appeared over time as it rotated. Most asteroids and comets produce a relatively modest light curve, varying by a small, predictable amount, as their somewhat irregular shape rotates in and out of view. Oumuamua's light curve was anything but modest. Its brightness varied by an extraordinary factor of roughly 10 as it rotated, the most extreme variation ever recorded for any object of its kind, before or since. To produce a brightness variation that dramatic, an object's shape has to be dramatically elongated, far longer than it is wide. Based on this data, astronomers calculated that Oumuamua's length-to-width ratio was somewhere between roughly 6 to 1 and 10 to 1, depending on the exact model used, and possibly even more extreme according to some analyses. To put that in perspective, imagine an object roughly the length of a football field, or longer, but only as wide as a large truck. Nothing observed anywhere else in our own solar system. No known asteroid, no known comet, comes remotely close to that kind of extreme elongated shape. Early public illustrations, including some released shortly after the discovery, depicted Oumuamua as a long, cigar-shaped object, and that image quickly captured the public imagination, appearing in headlines around the world. Later, more detailed reanalysis of the original light curve data introduced some healthy scientific debate about the object's precise shape. Some researchers proposed that rather than a cigar, Oumuamua might have actually been shaped more like a flattened disc or pancaked, still extremely elongated when viewed edge-on, which would still explain the dramatic brightness variations, but geometrically quite different from a cigar. This debate about Oumuamua's exact three-dimensional shape has never been fully settled, precisely because the object was only observable for a matter of weeks before it became too faint to study further, and no follow-up observations will ever be possible since Oumuamua is now permanently departing our solar system, headed back out into interstellar space. What almost every analysis agrees on, however, is that Oumuamua's shape was genuinely extreme by the standards of anything previously observed. Elongated, far beyond what's typical for objects shaped primarily by the ordinary physical processes, like gravity and rotational stress, that govern how asteroids and comets usually form. Beyond its shape, astronomers carefully studied Oumuamua's color and surface characteristics using spectroscopy, analyzing how the object reflected different wavelengths of sunlight. The results showed a distinctly reddish coloration, similar to certain classes of asteroids found in our own solar system, and also similar to some icy bodies found in the outer reaches of the solar system in the region known as the Kuiper Belt. This reddish coloring is generally attributed to a process astronomers call space weathering. Billions of years of exposure to cosmic radiation gradually altering and darkening the surface chemistry of an object's outermost layer, producing complex organic compounds that tend to reflect light with a reddish tint. The fact that Oumuamua displayed this kind of weathered reddish surface suggested it had likely spent an enormous amount of time. Specifically proposed that Oumuamua's unexplained acceleration, QLD, be explained if the object were extremely thin and lightweight, functioning almost like a light sail, pushed gently by the pressure of sunlight itself, rather than an object propelled by comet-like outgassing. It's worth being clear about where the broader scientific community stands on this idea. The overwhelming majority of astronomers studying Oumuamua, including most researcher S, who conducted the original detailed analysis of its trajectory, shape, and composition, consider the natural explanations, an unusual interstellar comet or asteroid fragment, likely composed partly of exotic ices, capable of producing subtle, undetected outgassing, to be far better supported by the available evidence and far more consistent with everything else we understand about how SH objects form and behave. Loeb's hypothesis received substantial media attention specifically because it was dramatic and captured public imagination, but it never gained comparably broad acceptance within the professional astronomy call community, largely because natural explanations, while still involving some genuine unresolved puzzles, don't require invoking an entirely new, currently unsupported category of phenomenon to account for the observed data. That said, the debate itself highlighted something genuinely valuable. Oumuamua was observed for such a brief window, with such limited data, that several aspects of its true nature may simply never be fully resolved with total certainty. The object is gone. It cannot be reobserved, remeasured, or revisited with better instruments in the future. Whatever uncertainties remain in our understanding of Oumuamua are, in an important sense, permanent uncertainties, baked in by the sheer brevity of the observation window we happen to get. Just 2 years after Oumuamua's discovery, in August of 2019, an amateur astronomer named Gennady Borisov, observing from Crimea, covered a second object on a clearly hyperbolic, unbound trajectory, the second confirmed interstellar object CT ever detected passing through our solar system. This object was named 2I Borisov in his honor. Unlike Oumuamua, Borisov's interstellar visitor behaved exactly like a fairly ordinary comet, displaying a clear, visible coma and tail as it approached the sun and showing a chemical composition broadly similar to comets found within our own solar system, though with some genuinely interesting differences in specific chemical ratios that suggested it may have formed under some different conditions than typical solar system comets. The discovery of 2I Borisov turned out to be scientifically important for an entirely different reason. It helped confirm that Oumuamua wasn't some kind of statistical fluke, and that interstellar objects genuinely do pass through our solar system with some regularity, exactly as theoretical models had long predicted. It also helped scientists appreciate just how unusual Oumuamua itself really was, since Borisov's comet behaved in a far more conventional, expected way, throwing Oumuamua's strange characteristics, its extremes, its lack of a visible tail, its unexplained acceleration, into even sharper relief by direct comparison. Since Borisov's discovery, astronomers have continued watching for additional interstellar objects, and in July of 2025, a third confirmed interstellar object, designated 3I Atlas, was detected, further reinforcing the growing understanding that objects arriving from other star systems are a genuine, ongoing, and increasingly well-due, documented feature of our solar system's environment, rather than a one-time curiosity. Even though Oumuamua itself is now permanently gone, having long since passed beyond the reach of any teles. COPE on Earth, its brief visit fundamentally changed how astronomers think about interstellar space and the broader galaxy we live in. Before 2017, the idea that objects from other star systems might occasionally pass through our own was largely theoretical. a reasonable prediction based on models of planet formation, but entirely unconfirmed by direct observation. Oumuamua changed that overnight, providing the first hard, undeniable proof that material GE genuinely does travel between star systems, carrying with it physical evidence, however limited, of conditions and processes happening in other corners of the galaxy entirely. Oumuamua's discovery also directly motivated new efforts, specifically designed to catch the next interstellar visitor earlier and study it more than, roughly, before it speeds away and becomes unobservable. The Vera C. Rubin Observatory, which began its major sky survey operations in 2025, is expected to dramatically increase the rate at which faint, fast-moving objects like Oumuamua are detected, potentially identifying several new interstellar visitors every single year going forward, each one offering astronomers a fresh opportunity to study material that formed around an entirely different star. There's also serious, ongoing discussion within the space exploration community about someday launching a dedicated spacecraft mission specifically designed to intercept and study a future interstellar object up close, rather than relying solely on distant telescope observations during the brief weeks such an object happens to remain visible. Various mission concepts, including a proposed European Space Agency mission called Comet Interceptor, are specifically designed with enough flexibility to potentially redirect toward a newly discovered interstellar object, should one be detected on a favorable trajectory during the mission's operational lifetime. Oumuamua, in the end, remains a genuinely open scientific story. An object we observed for only a matter of weeks, whose true shape is still debated, whose unexplained acceleration still lacks full confirmation, and whose ultimate origin among the countless stars of our galaxy will almost certainly never be pinned down with certainty. And yet, in that brief window in the autumn of 2017, humanity caught its first fleeting glimpse of a piece of another star system entirely, tumbling silently through our own cosmic backyard before continuing on, forever, into the depths of interstellar space. Somewhere out there right now, Oumuamua continues drifting outward, farther from our sun with every passing second, carrying whatever secrets it still holds about the distant star system it was, born in toward a destination and a destiny that no human being will ever know. Potentially hundreds of millions or even billions of years, drifting through interstellar space, continuously exposed to cosmic radiation, before ever encountering our solar system. At the same time, astronomers were watching closely for any sign of a visible coma or tail, the characteristic cloud of gas and dust that streams off a comet's surface as ice near the surface vaporizes under the heat of approaching sunlight. Despite Oumuamua passing remarkably close to the sun during its flyby, closer in fact than the orbit of Mercury, telescopes detected no visible coma and no visible tail whatsoever. Based purely on this visual evidence, Oumuamua was initially classified as an asteroid rather than a comet, since it appeared to behave like a solid, inert chunk of rock rather than an icy body actively venting gas as it warmed under sunlight. This classification, however, would soon be called into serious question by an entirely separate and much stranger piece of data. As Oumuamua continued moving away from the sun and out of our solar system, astronomers kept tracking its position as gravity alone could account for, a small but statistically significant anomaly published in a peer-reviewed paper in the journal Nature in 2018. For comets, this kind of behavior is actually fairly routine and well understood. When a comet approaches the sun, ice near its surface vaporizes and jets outward, acting almost like a tiny natural rocket thruster, subtly altering the comet's trajectory in a way pure gravity alone wouldn't predict. This is called non-gravitational acceleration, and astronomers have documented it in hundreds of comets throughout the solar system. The problem was that Oumuamua showed no visible coma, no visible tail, no observable sign of any gas or dust being ejected from its surface, the very thing that normally causes this kind of non-gravitational acceleration in comets. And yet, its trajectory clearly showed the telltale signature of exactly this kind of subtle extra push. This created one of the central mysteries surrounding Oumuamua, one that remains genuinely unresolved to this day. Most researchers studying the object lean toward an explanation grounded in ordinary comet-like outgassing, just happening in a way too subtle to be directly detected by available telescopes, perhaps because Oumuamua's ice was primarily composed of something other than the water ice typical in solar system comets. One prominent hypothesis, published by researchers Jennifer Bergner and Daryl Seligman in 2023, proposed that Oumuamua's surface could have been embedded with frozen molecular hydrogen, formed and trapped within the object over the course of its long journey through interstellar space, which could vaporize and produce thrust without generating the kind of visible dust cloud that normal comet outgassing typically creates. Other researchers have proposed alternative explanations involving other exotic ices or unusual surface properties entirely unique to an object that formed under conditions completely different from anything found in our own solar system. What virtually every serious researcher agrees on is that the trajectory anomaly is real, was measured carefully and repeatedly, and remains one of the most genuinely puzzling aspects of Oumuamua's entire brief visit. Given that Oumuamua arrived from interstellar space, one of the most natural questions astronomers wanted to answer was, which star did it come from? By carefully calculating Oumuamua's trajectory backward through time and accounting for the motion of nearby stars relative to our own sun, astronomers were able to narrow down candidate star systems. Hundreds of millions of years, drifting freely through interstellar space before ever reaching our solar system. Across that span, its trajectory would have been subtly nudged and altered many times over by the gravitational influence of other stars it happened to pass near along the way, erasing any clean trail back to a single point of origin. This uncertainty points to something important about Oumuamua's likely origin story more broadly. Most researchers believe it was very likely ejected from its original home star system billions of years ago, possibly during that system's early formation period, when gravitational interactions between newly forming planets can fling smaller bodies, asteroids, comets, planetesimals, out of a star system entirely, sending them drifting alone through the vast emptiness of interstellar space for the rest of their existence. Based on theoretical models of planetary system formation, astronomers strongly suspect this kind of ejection process happens routinely throughout the galaxy, and that interstellar space should, in principle, be filled with countless similar objects, the discarded debris of planet formation from billions of different star systems, drifting silently through the galaxy for eons. Oumuamua wasn't necessarily some unique, one-of-a-kind object. It was, more likely, simply the first such object that happened to pass close enough to our own solar system at exactly the right moment for our telescopes to actually notice it. No discussion of Oumuamua would be complete without addressing the theory that generated by far the most public attention and media coverage, the suggestion that Oumuamua might not have been a natural object at all, but some form of artificial technology. This idea was most prominently advanced by Avi Loeb, an astrophysicist, and at the time, chair of Harvard University's astronomy department, who published both academic papers and a popular book arguing that several of Oumuamua's unusual characteristics, its extreme elongated shape, its unexplained non-gravitational acceleration, its reddish coloring, were at minimum consistent with the possibility of an artificial origin, potentially even a probe or fragment of technology from an advanced extraterrestrial civilization. Loeb,